welcome everybody. I hope I'm broadcasting to you. This is Dave Waits. I'm with Pia Sorensen and Michael Brenner. This is the first lecture of our Science and Cooking lecture series, and this is the first time that we've done it virtually. And please bear with us as we learn how to do this. We hope that you enjoy it. This is a lecture that is associated with a class that's taught at Harvard School of Engineering and Applied Sciences on science and cooking, from Haute Cuisine to soft matter physics. This is, I think, the 11th year that we've had it. These public lectures are sponsored by several different organizations: Gastronomy Solutions, Escada, 1933, Harvard MRSEC, SAMIC, Shimadzu, and Broad & Taylor. And tonight, as always, we'll start with an introduction of the science. Tonight, we won't have so much introduction of science because our speakers are themselves scientists. But usually in these lecture series, we start with about 15 minutes of the kind of science that we do in the class that week, and what we're going to do with our students, but also as a way of introducing the chefs who will talk about the same basic subject matter of the class that week. So instead of doing that, maybe I give you a bit of a background of the class itself. It started out, I think, 11 years ago. And this is a scene. The class, and this is a science class, and people don't line up for science classes at Harvard, but they did.
Let's try to, so again, I repeat, there are some seats. I don't know, I'm not exactly sure what you're supposed to do in a situation like this, but I just point out that there are some seats a little bit further. If some of you could move up, more people will get in.
People line up and crowd the classroom for science classes. But for this class, they did, and that's because it combines the science and cooking. And cooking, of course, is something that we all love, we all know. And in fact, we developed a few traditions. I apologize, my sound doesn't seem to play. So I'll have to just narrate the sound. This is Michael, the first week, giving a lecture, and this is a science class. It is about cooking, but it's a science class. So every week we have an equation of the week.
These must be equal.
And here's Michael explaining the
it must be the case where motion and sticking are an exact balance.
He tells us what it is, and
that's
then he turns around and he says, you're all supposed to clap. And that's a tradition. We always have an equation every week, and everybody should clap. And so those of you listening on Zoom, please join in and please do clap. Another tradition that developed more spontaneously, we had Joan Roca, one of the best chefs in the world. His restaurant, Can Roca, near Barcelona, was voted many times the best restaurant in the world. He and his two brothers, he came, each of his brothers have come. And he came and he was making a very, very special dessert. Here he's assembling everything. And before he'd shown us where he'd taken some water. And this is the water. You see it's liquid. He had put it in a refrigerator. It said -5 degrees C. Poured it out. It solidified. And everybody just, and then spontaneously broke out into fire. So that became a second tradition in the course, that is, that when we see an amazing dessert, we clap. Great. So this was 10 years ago or 11 years ago, and we've been doing it ever since, having a lot of fun, working with a lot of people. And maybe I'll turn it to Pia to introduce somebody who's been with us, and very fortunately for us, he's been with us right from the start. There was only one possible textbook at the time, and that's Harold McGee. And maybe, Pia, you could explain a little bit about the books and how we have Harold. We're so honored to have him as part of the class.
Yes, thank you, Dave. So this is actually a slide from 2010, from the very first lecture. And as you can see, it says, this will be the only required textbook for the course. And this was on food and cooking with Harold. And ever since the first year, Harold has come back every year to introduce the class, just like he's doing this year. So I'm going to come back to Harold and his books. But before that, I want to say a few things because, so all of this was in 2010. And since 2010, a lot has happened. And one of the things that has continued to happen, if we could have the next slide, is that we have every Monday night in the fall semester, we have continued to gather in the Science Center at Harvard. And I suspect that there are some people in the audience who used to join us for those lectures, and maybe this year you're joining us on Zoom. But as you know, this used to be a buzzing lecture hall filled with people, action-packed, people from the Boston and Cambridge general public coming together to enjoy these lectures. A lot of action, and actually twice, we've had to evacuate the entire science center because the fire alarm went off because the cooking was so intense. So I think one of the, maybe one of the advantages of doing this over Zoom is that despite all the technical difficulties, at least we do not have to worry about fire alarms, we think. So the public lecture has been going on, and in 2013, which is the next slide, we converted the course to an online course on edX. And we were, at the time, we were very excited. We traveled around the world and visited the different restaurants of the chefs, and we had them explain the food and the science in their kitchens. And as you can see, I traveled to one of these restaurants with a microscope in hand. And then we interspersed these videos, if you can click the next thing. We interspersed these videos with science videos, explaining what was going on in the kitchens. So that was in 2013. And this year we have a new surprise on the next slide, which is that for the last several years, we've all been working very hard on a book. And the book finally is coming out this fall in October with Norton. And this is the cover. This is actually a vanillin molecule on the cover. And I think there's going to be a link to the book if you want to pre-order it. There's going to be a link to the book in the chat that you can click on. So that sort of brings us into this year. And this year we have a beautiful lineup of chefs, which is showing up on the next slide. So after Harold and Dave this week, next week we will be joined by Joanne Chang. For those of you who are from the Cambridge-Boston area, you know that Joanne Chang's Flour Bakery and Cafe is sort of a Boston institution, and she has been joining us every year. So if you're not, if you're from the area, you should come back and enjoy it again on Zoom. And if you're not, this is a real science and cooking classic. So that'll be fun. That's next week. The week after that is Lois Ellen Frank. She is really interested in the science of Native American cooking. So she's going to tell us about that. Marieke van Beurden is a master chocolate master. She has won various chocolate prizes. So she's going to make chocolate on Zoom. Sadly, there are no tastes, but you'll see the beautiful textures of the chocolate. Nina Compton is coming the week after that, and she is going to tell us about her perspective on Afro-Caribbean French-influenced food. And then we have a little bit of a break, and then after that, Jose Andres is coming you probably know of Jose Andres. He's usually out saving the world in various places, but he's also a fantastic educator, fantastic chef, and he is going to come and tell us about that. And then Andoni Aduriz and Ramon Perisset at Meteorites, they will join us during fermentation week. So one of our topics of the semester is fermentation. And Meteorites in Spain is really one of the most creative places in the world in terms of using fermentation to create new flavors and new sort of innovations in food. And then we're rounding off the semester with Garima Aurora, who is joining us from Bangkok. And she is very interested in using various traditional Indian techniques and kind of marrying them with new approaches to food. So we're going to explore the science of that. Okay, so that's the chefs. And there is one more development over the last 10 years, which brings us to the next slide. So as Dave told you, we started off this course in 2010, very excitedly being able to use Harold McGee's book on food and cooking as the textbook for the course. That was in 2010, now it's 2020, and Harold has been hard at work on his next book, which is this Nosedive, a field guide to the world's smells. And I think we're going to get a little bit of a taste, a little bit of a sniff, maybe I should say, a little aroma from that during today's lecture. So and I think there's going to be a link in the chat for that as well. So that should bring us to our last slide, which is the introduction of Harold and Dave Arnold. So Harold and Dave have been coming together, sort of kickstarting this lecture for the last 11 years. And this year, I think we'll get a special introduction to Harold's new book. Also, in addition to on food and cooking and Nosedive, also author of Curious Cook. It's always a huge pleasure to be able to introduce him to this series. And he is joined by Dave Arnold, host of Cooking Issues, founder of Booker and Dax, the bar in New York, and the director of Museum of Food and Drink in New York City. And he usually brings a lot of action-packed demos. And I can see that he's been prepping during this introduction. So I think there is some of that to come. So with that, you can't see us, but we should all join and clap and welcome Harold and Dave.
Let's see. Well, I haven't done many of these Zoom things, so is it okay not to share quite yet? Can I just talk?
Yes.
Okay, good, because that's what I was going to do to begin with.
No
just
problem.
To thank you and Pia and Patricia and Michael and everyone who's been involved in this class from the very beginning, because it's been great fun for me and an honor to be able to participate. And I do want to give you today a whiff of the quirky book that I've been working on actually ever since I started joining you for the course, since 2010. So, and I'm delighted to notice that we share the exact publication date, your book and my book, coming out on October 20th. So fantastic. Anyway, this book is it's a quirky book, and it's not mostly about cooking, but cooking does enter into it. It's about smells. And the reason it's about smells is it started out as a book about flavor. Then I focused in on smell because smell is so much the dominant force in flavor. We have taste receptors for maybe a dozen or so tastes, but for hundreds and hundreds of aromas. So I focused in on aromas, and then realized when I began to look into them that they were really interesting. So aromas are stimulated by volatile molecules, molecules that can fly in the air and get into our nose. And it turns out that foods share volatile molecules with lots of other things in the world. And that really caught my attention. And I just went down a rabbit hole to see what all those molecules were doing out there and what they told us about the world. When I was a kid, the thing that actually got me interested in science, Dave very kindly called Dave and I scientists. In my case, not at all, but I've been fascinated by science from the very beginning. And what really got me interested was standing out on winter nights, looking up at the skies, seeing Orion, reading about the universe, about this tremendously old, tremendously just inconceivably energetic and complicated and fascinating place. And I ended up in writing this book about the smells of foods, going back to that interest and actually writing about the smells of Orion and things like that. So what I want to do is give you just a little taste of that. The original catalog classification for this course was SPU 27, Science of the Physical Universe 27. And what I'm going to try to do is just give you very quickly a sketch of the place of cooking in the physical universe. And I'm going to throw a lot of molecules at you and a lot of stars and things like that at you, lots of odd things that don't seem at first to have much to do with cooking. I want you not to worry about that and just let them, fly by. I don't want to impart information tonight. I just want to give you a sense for the place of cooking in the overall big scheme of things. So nothing of practical value in this, but Dave will take care of that when he takes over, because he'll be talking about what cooks do and don't know about the application of energy in the kitchen. And that's the title that I gave to this talk of mine, Nosedive into Pyrolysis, because that's really the key process for generating flavors in the kitchen. It comes from two words, two Greek roots that mean fire and to release or to break or to let go. The association with fire is unfortunate because fire is combustion. Combustion involves the action of oxygen, and pyrolysis is actually the transformation of matter by means of heat alone, organic matter in particular, without the action of oxygen. And pyrolysis makes combustion possible, but it also gives us some of the wonderful things that we enjoy when we eat, and that actually hark back to other places and other times. So with that, I will try to share my screen. And I hope you can all see Dave. I'll assume I am, because I'm not hearing any response. I guess that doesn't easily happen on Zoom. So the subject of the talk is a nosedive into kitchen pyrolysis. And that's Dave with pyrolysis gases coming very close to his face. A couple of basic things to begin with. So smells are really important in enjoying food. They are triggered by small molecules, as I mentioned, that can fly through the air and interact with our olfactory receptors in the nose. They might fly through the air from outside. They may fly through the air inside our mouths, and that's how we enjoy the flavors of foods that we're actually eating. And the molecules have to be on the small side, because if they're too big, they're just too heavy to fly in the air. And there are other characters that help define what volatile molecules can be, but this is a representative handful. And we tend to name them apart from the chemical names and describe them according to the source that we usually find them dominant in. So in the case of pinene, for example, it got that name because it was extracted from and smells like pine trees. Vanillin, same thing for vanilla. In other cases, it's not so clear. Hexanal, cut grass, octane, familiar from gas stations, and that's because it's a component of gasoline. Ammonia, familiar from cleaning agents, and so on and so on. Now, the details of the molecules, as I say, are not important. And in fact, what I'm going to do is rely on cartoons of them, because they all, or almost all, have carbon and hydrogen atoms. And so you can kind of indicate them by the corners and the ends of lines, and just leave them out and see much more clearly the basic architecture of the molecules. So here's, again, what they look like with all the bonds shown, and then clearer when the carbons and hydrogens are cleared away. And I'm going to be pointing out just similarities in shape and in motifs as we go along. So, as I say, I fell in love with science through astronomy. And so I decided to go back to the beginning and ask where, if you were a lover of volatiles who could fly through the air or through space and sniff around the universe as it was forming, when would you and where would you first begin to smell things that would be recognizable here on Earth? And so, of course, the chemical elements are cooked up in stars or in the neighborhood of stars. And then some of those elements react with each other in interstellar space to form molecules. And this is that constellation Orion that I told you I was so enamored of when I was a kid. And if you look below those three stars, you see a nebula. And it turns out that that nebula is a place where there are a lot of molecules being formed. And when you get this close-up picture of it, you see that there are swirls of gases, swirls of dust, all kinds of different temperatures and pressures and velocities of materials, just lots and lots of different physical conditions in which atoms can find each other and then decide whether they want to have anything to do with each other. And the way astronomers, cosmochemists figure out what's up there is essentially by looking at the wavelengths of light or radio waves or infrared and seeing what kind of light is being emitted from places like this, what kind of light is missing, is being absorbed in different parts of this kind of nebula. And that gives you information about what the chemical materials are there without our having any hope of actually getting there and taking a sample. So every few years, there's a census of the molecules that have been detected by those means in space. And the last one I could find was in 2018, 204 molecules at that point, ranging between 2 and 70 atoms. And by far, the dominant element in those molecules was carbon. It was in even more than hydrogen, and there's way more hydrogen in the universe than there is carbon. And I just want to give you a sampling of some of the molecules that astrochemists have detected out there in the Orion Nebula and Sagittarius and elsewhere. Of course, most of them are very small, simple molecules. So ammonia, hydrogen sulfide, which is the smell of freshly cooked eggs, but in excess can be really unpleasant. And then methane, which has no smell, it's natural gas, but it's an important player in the molecules of the universe. A few other examples: benzene, I'm showing it here both in its, showing all the atoms and bonds and so on, and then the simplified version, just the ring, and then naphthalene, which is essentially two benzene rings fused together. Both of those smell like solvents because that's where we usually encounter them. And then we don't ever smell rugby balline, but that's just to give you a feeling for the versatility of carbon in forming molecules. It is the element that does best at playing well with other elements and with itself. And so it's able to form these wonderful structures out there in space with no help from us or engineers or anything like that. It does it itself. Now, in the methane family, there are a number of versions of it where one of the hydrogens is replaced by a different group. And I've highlighted nitrogen and sulfur because they generally lend a not so nice note to whatever it is they find themselves in. So methane thiol smells like rotting vegetation because we find it there. Methylamine smells fishy because it smells like fish that's gone off. But then we get to more pleasant things. Methyl alcohol and ethyl alcohol smell like alcohol. Not necessarily pleasant, but at least, they're very, very common molecules, ethyl alcohol especially, in our everyday lives. And then acetic acid, the smell of vinegar is out there. And acetaldehyde, the smell of green apples. And methyl acetate, which is a common ester found in many different fruits. So fruits, and apples and vinegar, alcohol, I think of those as organic, as coming somehow through some process from nature, from growing things on planet Earth. But in fact, all of these things are out there with no help from plants or anything else living. Now, all of those molecules were detected at great distances, light years distance. Sometimes we get deliveries from interstellar space to the Earth, and those are really valuable because then we get to see all of the things that we're missing detecting out there in space. So there are lots and lots of asteroids out there, and occasionally they become meteorites and collide with the Earth. And usually they burn up, but sometimes they don't. And when they don't, they can be analyzed. One of the most important has been the Murchison meteorite. It fell in Australia 50 years ago last year. And it's been analyzed and analyzed and analyzed. And it turned out to be really fascinating because it contains all kinds of molecules that are more complex than can be detected by infrared and radio astronomy in nebulae. They're preserved in the meteorite and then carried down to us. And of course, great efforts are taken to make sure that the meteorite material hasn't been contaminated by anything here on Earth. And what do you find? Well, the origins of life scientists were very excited because they found the materials for making DNA and for making proteins, amino acids, and for making membranes, fatty acids. But I was really interested in the volatile molecules that they found in the Murchison meteorite, and here are some examples. Some of them not so pleasant, but all of them familiar from life on Earth, and one of them actually kind of ethereal. Phenylacetic acid is floral. Benzaldehyde is the typical smell of almond essence. And you notice how at this point we're beginning to see not just simple chains and rings, but longer chains, and then chains and rings joined together. into things like phenylacetic acid, which has a very particular and pleasant aroma. So somehow the conditions inside the meteorite is either conducive to the formation of these more complex molecules, or simply traps them and allows them to survive and be detected in a way that's not possible in space. So one of my favorite writers on the astronomical side of things, astrophysics, is Hubert Reeves, who's a Canadian astronomer. And he has this wonderful sentence: carbon will play the game of complexity on a grand scale. You know, beginning with its formation in stars, and then beginning to form more complex things in nebulae, and even more complex in meteorites. And then on Earth, it becomes what he calls the greatest hero of chemical and biological evolution. I like that idea that an element can be a hero in the story of the universe. Anyway, so carbon is exploring complex structures and systems on planet Earth pretty much from the moment that the oceans stopped boiling and molecules could begin to, carbon could begin to explore the possibilities of making more complex molecules. As I say, the Murchison meteorite contained the raw materials for the most important molecules in living things: DNA and proteins and membrane lipids and structural materials like cellulose and lignin in plants. So there's a lot there, and that's kind of the story of the evolution of life, is from relatively simple and small creatures, archaea, bacteria, and so on, to the panoply of the living world that we know today. That's all wonderful, but those larger molecules are actually useless when it comes to the enjoyment of our sense of smell, because of course they're all way too big to be volatile, so they don't fly through the air and get into our noses and stimulate us. But the basic metabolism of all living things generates byproducts that are small enough that we can detect them. So DNA, proteins, carbohydrates, fats are all constantly being repurposed, broken down into their building blocks, energy extracted from them, and then rebuilt into other things. And then just to point out that DNA contains nitrogen, proteins contain nitrogen and sulfur. Remember what nitrogen and sulfur were like in interstellar molecules. And this is the kind of picture that you can begin to draw when you consider the volatile products of basic living metabolism. And the most enjoyable aspect of this, of course, are the products of microbial metabolism that we choose to cultivate. That is to say, fermented foods and drinks. And these are just three examples of sets of molecules that have very particular and recognizable smells. The winey smells are different kinds of alcohols. The vinegary smell, of course, is acetic acid. The cheesy smells are these short chain fatty acids, and sulfur molecules, which in other contexts can be really unpleasant, but in the context of chosen, cultivated, made foods and drinks can lend a nice additional dimension to the flavors of foods. So that's one level. Another is spoilage. So wild microbial metabolism, just uncontrolled, unshepherded, it's just happening. Rotting, decay, smells like that. You actually end up with all the smells that you also get in cultivated products, but others that, that cultivators find a way of avoiding. So there's fishy trimethylamine, there's fecal scatol, cadaverine, which kind of speaks for itself, all of them nitrogen-containing molecules, the products of protein and DNA-based backbone, DNA-based molecules. And then there's our own microbiome and its metabolism. The human body does generate volatiles from its own metabolism, but they pale in comparison to the metabolites of the creatures that are outriders and inriders. And so the smell of our breath, the smells of our bodies, the smells of the things that we release from our bodies, all of these things are generated by microbes. And they include any and all of the structures above and others. So depending on the particular material and the particular microbes that we happen to be harboring in that spot. So metabolism breaks these large organic molecules down into small ones that can smell, and they're mostly not so nice. Heat will do the same thing, and heat under different conditions will give different results. So here's a recipe for pit-cooked, slow-cooked, pressure-cooked organic materials, which is to bury those materials deep in the earth and simmer at actually pretty moderate temperatures, cooking temperatures, but for millions of years. And what that gives you is coal and petroleum and gas. Petrochemicals of all sorts, many, many variations on carbon chains and rings from the smallest to the largest. Here are just a few of the ones that are most familiar to us. Oxygen will also break large organics into smaller molecules, volatile molecules, gaseous molecules, but generally speaking, they're too small. So if you burn organic material by means of lightning or a spark, and we're getting way too many of these smells out here in California these days, what you get is a lot of heat and light energy and a residue of ash, but also carbon dioxide and water are the end products. Carbon dioxide is indeed a small carbon molecule, but it's so small that it's not really interesting unless you're a lover of carbonated beverages, as Dave is, and I am as well, in which case it gives you a nice tingle. But when you're cooking, carbon dioxide does not thrill the nose. The case has been made, and I think it's been made very well, that fire was terrifically important in the development of our species. The thing is that what fire provides is the energy to do pyrolysis, which is what gives us the deliciousness of food cooked on fire. So along the way to combustion, to the formation of carbon dioxide and water from organic materials, is pyrolysis, which is the breakdown of complex molecules into simpler ones simply by virtue of heat, without the involvement of oxygen. And simply looking at a match flame, you can see that there are various different zones of activity, different things going on in different places. And that's a clue, which in fact, Michael Faraday lectured and wrote about in 1825. That's a wonderful little book that's still worth reading. What those different colors indicate are different processes going on in the head of the burning match. And so very briefly, what happens is that oxygen is available for combustion only at the surface of the material. And so you do have combustion at the surface. It heats the wood under the surface, but there's not any oxygen down there for combustion to continue. So what happens is that the wood underneath the surface begins to pyrolyze. It heats up and it begins to break down. In the process of breaking down, it forms all these different smaller molecules, and those molecules are what those molecules are the molecules that actually combust when they reach the surface of the wood. So they react with oxygen to form carbon dioxide and water. And so what you can do, what people have done actually fairly recently in the last 15, 20 years, is to look at the pyrolysis products that come from wood. And wood is this combination of lignin and cellulose, lots of carbon rings and short carbon chains joined together. And it turns out that over a temperature range of 400 to 3,000 degrees Fahrenheit, you end up with this panoply of different molecules and smells, from simple things like vinegar, which we found in interstellar space, to molecules with oxygen in the ring, which have bready and sweet aromas, to carbon rings that do have oxygen decorations, but none in the rings themselves. And notice in that central column, along with the two smoky molecules, syringol and guaiacol, are eugenol and vanillin. They smell like clove and like vanilla because they're identical with the molecules that cloves and vanilla make for their own purposes without the help of pyrolysis. And then at those higher temperatures, when molecules are really being stripped of all their decorations, you end up with things like cresol, which is tarry in smell, and then benzene and styrene, which are those solvent aromas. So that's what happens when you burn wood. The thing about burning wood, unless you're doing it, you're barbecuing and you soak wood chips and you slow down the pyrolysis process to try to capture some of those interesting aromas. What happens usually when you light a match is that all those interesting molecules just go up in smoke. They're very quickly oxidized by oxygen when they leave the match, and we only get the barest hint of them. So what cooking really is an expansion of that chemical space that usually just disappears very quickly, an expansion of its lifetime so that we can savor those molecules in the cooking that we do and accumulate them and focus on them and find ways to enhance their production as opposed to the other things. So the simplest version of pyrolysis I know is the caramelization of sugar. And way back 10, 11 years ago, one of the first demonstrations we did in the course was to make some caramel at the front of the lecture hall. And within a few minutes, people at the back of the lecture hall could smell the wonderful aromas. And that's because pyrolysis does wonderful things to sugar. Sugar is not that different from cellulose in wood. And so you end up with all the same products of relatively low pyrolysis temperatures, although there is cresol down there at the bottom. But then in addition to those, because more care is being taken with the process, you end up with all kinds of things that either don't get noticed or just go up in flames before there's even a chance to notice them in the case of ordinary pyrolysis. So cheesy, mushroomy, citrusy, strawberry, caramel, coconut aromas generated from this simple molecule, simple sugar molecule, by the force of the force and the chemistry of heat and pyrolysis. And not only that, but pyrolysis is able to redeem nitrogen and sulfur. Remember, we've seen several examples of molecules that contain nitrogen and sulfur that are less than nice. Well, if you pyrolyze protein-rich things like meat, like seeds, coffee beans, cocoa beans, what happens is that you end up with very different looking nitrogen and sulfur compounds. Some of them joining forces with some of those pleasant oxygen containing rings. And these molecules are wonderful. They're in fact what give meat and meaty things like coffee and chocolate their particular kind of note, that roasty, savory kind of aroma that most plant foods just don't develop. So I hope this hasn't been too much of a strain, and that the molecules haven't been too dizzying, and that you have a sense now for why it is that it's worth taking a closer look at what's going on in pyrolysis, and as Dave is going to do, get better control over how it is that we bring heat into our foods and generate aromas with them. So that's it. Thank you very much.
All right. Hey there. I hope you guys can hear me. Thanks so much for having me again. And Harold, stick around. You may need to unmute when I'm using the blender to say stuff so that they're not just listening to blenders. I have a lot of kind of technical back and forth, so you're going to have to bear with me. I'm going to try to go between my infrared camera and my screen and a couple of other things, so hopefully we can make this work. As Harold said, I'm going to be talking mainly about fire and heat, but Professor Waits wanted me to start with one of his favorite demos that we have done over the years in the student class that we don't do anymore because of alcohol and students. And so I'm going to do his quick favorite demo because he really wanted me to do it. And afterwards, I'm going to make a quick drink, and hopefully Harold can, and Dave and Pia and everyone can, get a drink and drink along. Maybe you can at home. Let me share this camera. Let me see here. Share screen. All right. Now, hold this. I need a picture of this. Now you see how this thermometer here says it's about 5 degrees Celsius right here. What this is in is just in a bucket of ice water. And what the demo here is that back in the day, everyone used to ask, well, what temperature is it? And this is all in my book, Liquid Intelligence, by the way. I'm going to be talking about the next book I'm working on, but this is all from Liquid Intelligence, my book. You can buy it at any fine book reseller that you wish to. So one of the things is that when you make a cocktail, well, what temperature is it going to be? You're going to take ice, and that ice is going to be at 0, and I'm proving that I've had this thing soaking in water since before the lecture started. And this is vodka, and I'm going to stir them together. And the question is, what temperature? Right now, the vodka is probably around, I'd say 20-something Celsius. I'm not going to take time for it to get all the way up to temperature. You get closer to it, Jim? Yeah, about 20, 21. And the water was reading 5 before, but that's just because you can't really trust on temperatures being accurate unless there's motion. So if you stir it, you'll see that it's going to go down very quickly to, if I hit 1, I'll be happy, because in the scheme of the accuracy of this cruddy little thermometer, 1 is fundamentally 0. So then I have this ice, which we now know is at roughly 0, and we have this, which is about 20. Let's take some of this ice. I'm going to drain it in my hands, which is not cool cocktail technique, but there you have it. I'm going to add some ice. Add a little more. And now let's start stirring, and let's see where we get. 14, a little glare there. 13, 8, 7, 6, 5, 4. Do you think it's going to stop at 0? Do you think it's going to stop at 0? Do you? 1. Oh, real 0, which is actually below 0 on this crappy thermometer. Let's go. Come on, come on. I know you can do better. Oh no, the stupid thermometer won't go below 0. But it did go below 0. It says low because this thermometer can't go below 0. What's happening here? In fact, I could stir this thing down to about -3, -4. My thermocouple thermometer is broken. I can't get it to work. Sorry, technical difficulties. But what's going on here? Well, what's interesting about it is you're taking something that's at 0 degrees, something that's well above 0 degrees. You're mixing them together without adding any heat to it, right? So there's no heat in and there's no heat out, roughly, right? We're calling this a sealed system, a contained system. So really the only thing that's left is there's a major entropy change as the ice melts. The ice really, really, really wants to melt into the alcohol to dilute the alcohol and increase the entropy of this drink. And the only way it can do that is by melting the ice. And the only way it can do that is by adding heat to the ice. So the entire system has to get colder. And this is why, even though you're starting with materials that are all at or above 0, you can shake a cocktail or stir a cocktail and get it well below 0. The nitty-gritty details are all in the book Liquid Intelligence. In the meanwhile, so this is gonna average, we'll get down to about -2 if I stir it long enough. Most real bartenders are only getting it down to about 0, -1. But in a shaken cocktail, almost all of us get it down to about -4, -5. So I'm going to make a shaken cocktail using a technique also in the book called blender muddling, where we're taking herbs. In this case, a very fancy, a little long in the tooth. It's a little bit old, but a fancy herb called scented geranium. This is a rose geranium, which is not actually a geranium plant, strangely. It's a pelargonium plant. Who knows? But I picked this because I was reading, when I was reading, I had the pleasure of already reading Harold's fantastic book. He talks about all of the interesting, the 4 or 5 pathways that plants use to make interesting aromas. And this has a very, very interesting aroma of roses and lemons and citrus. So I'm going to mix this with Cointreau, which is an orange liqueur, gin, a little bit of simple syrup, and some lime juice. I'm going to blend it. The herbs will get all blended, turn green. I will then pour it, shake it, and then I'll make a drink for my wife and myself. And then I'll continue with the rest of the demo. So Harold, if you're still there, do you want to say something about geraniums? And you want to mute me for a second because it's going to get real loud. You can unshare that. It's so strange doing demos without any sort of feedback of people there. You know what I mean? It's very strange. All right. So you can see that deep, deep green color, I hope. What? I don't think Harold's saying anything about pelargoniums, but let me see. All right. All right, so while I'm making this drink, if Harold's not talking, while I'm making this drink, I will talk about what I'm actually here to talk about. And that is 2 projects that I'm working on right now. One is the next Sears All, which is one of the products that Booker and Dax makes, which I showed you before, which turns a torch into a handheld broiler. And the other is my next book. And my first book, Liquid Intelligence, is all about cocktails, but my second book is all about cooking. And one of the things that I have to do anytime I write a book is start from the very beginning of everything I think I know and then redo it to try to see whether what I know is correct. So I've started doing that in terms of how cookware works and how thermometers work. And so we're going to talk about that in a second. So this drink, I don't know if you can hear me, this drink is called Lady's Border. And the reason it's called Lady's Border is because I learned about scented geraniums at the New York Botanical Gardens Lady's Border, which is what that thing is called, where if you're ever in the area, it's an incredible place to go. And it's just a beautiful garden filled with all sorts of both visually stunning plants and culinarily useful plants. So because I learned about scented geraniums. And scented geraniums, by the way, if Harold's not going to come back, there are millions, not millions, there are hundreds of different kinds of scented geraniums. So geraniums can smell like roses, they can smell like lemons. Some people say they can smell like nuts, but the ones that smell like nuts don't really smell like nuts. Some of them smell bad. Interesting. Anyway, ladies' border. If you have a scented geranium in your yard, I recommend doing vouching. Okay. And you're never going to get a color as green as that using any technique, well, unless you have a liquid nitrogen, other than blender modeling, which, as they say, you can learn about in the book. So now on to temperature. So I have two main problems. This is the classic Sears All that I make. So what happens is a flame is going through here into this cup and then heating this up, and it's converting the direct heat flame of the thing into radiant energy, right? And we're going to talk a lot about radiant energy in a second. But you see it's rather small, and so like what I wanted to do was make one that was slightly bigger that had a larger area. But I was having a lot of trouble trying to figure out, other than just kind of running some tests, what the difference between these two is. So I wanted to figure out a way to measure the temperature on these two things. But the problem is there's no real such thing as the temperature, right? And I'm going to do some experiments to show you kind of what I mean later on. But with this one, I think you can see as it's going, you see a lot of flame. I don't know if you can see it coming up over, right? So in addition to the radiant heat, there's actual still flame coming out of the front. Whereas on this larger unit, there's still some flame, but there's much less. And since this is designed to be mainly a radiant heater, a radiant boiler, I wanted to figure out whether there's some way that I could actually test that and see what's going on. Now, if you want, this thing gets to be at least on the surface 1200 degrees Celsius, in that range. If you want a thermal camera, and this is a cheap consumer brand of a thermal camera. If you want a thermal camera that can do that can take that kind of picture, you're going to need to spend a lot of money. And let me show you. Let me share my screen here. And this one is like, you know, the $300 Amazon special. But let me just share my screen. Okay. And then you look, but you have to. I'm going to show you this because it's relatively complicated. I'm going to try to show you a couple of quick demos so that you can understand what an infrared thermometer is actually doing. So a lot of people use, and I hope you can still see me, a lot of people use these things, these infrared thermometers. But it's very hard to understand what you're actually looking at, what you're seeing. And so in order to better visualize that, using a thermal camera to better understand what's going on is going to give us a much clearer view. So if you look at this graph that I'm showing you, what's going on here. So what this is a graph of the radiation that is coming off, the electromagnetic radiation, right? Think of it as light. Basically, all of these things are optical systems, but instead of running in the regular kind of visible light range that we think of, they're optical systems that are running in the infrared. So you can't see them, but they are in fact optical systems. So they're not measuring temperature. That's one of the main mistakes I think people make. You're not measuring temperature with an infrared thermometer. You're measuring a proxy for temperature, and that proxy is how much infrared radiation is coming off of your item. So if you look at this graph, this is a graph of kind of, there's a thing that we're going to get into here called a perfect black body. Now, a perfect black body doesn't mean that it's black in the terms of it's black like black when you look at it. It means that anything that it is a perfect emitter and also a perfect absorber of radiation. So this is a set of curves for different temperatures in Celsius, thank goodness, so you don't have to do that wretched Kelvin thing in your head. But what it shows is that as you increase the temperature of the thing that you're looking at, right, not only does the amount of radiation increase, but also the peak of it shifts over. So what an infrared thermometer does is measure a fairly narrow band of the infrared, right, in here. This is where the visible light is. This measures approximately in this band here, which takes care of almost the peaks of these curves are kind of all kind of well within of the cooking temperatures we look at, are well within the range of the peaks of these things. And then it integrates how much energy it's getting from each individual pixel. Each pixel in the camera is integrating it, and then running an algorithm to determine, based on the integral of how much energy it's getting, which one of these temperatures it's looking at. And that's all it's doing, right? So it's an optical system, and then you can focus it, it can be focused, and that's actually kind of the first kind of thing that people do wrong, is that, I don't know if you can see me, but let me stop the share for a second. So people will take their thermometer, right, and they'll shoot it. Can you see this? Is the laser on me? So they'll shoot it at something, and they'll see this like single laser dot. I don't know if you can see yeah, there you go. See the laser dot, right? And they're like, oh, I'm taking a picture of that. Wherever the laser dot is, that's what I'm taking the temperature of. Well, no. In fact, it's an optical system and it's focused. So you're much better off. And I've seen like the most famous chefs, the smartest people, even science people, people who are taking your temperature because of COVID. Everybody somehow thinks that they're taking the temperature where that laser pointer is, when in fact it's like a cone that, and usually on the side of your thermometer, there's a picture of the cone that it's taking. It goes like this, and the further you get away, it's just a huge thing, and it's just averaging kind of everything. Now, if you get real up close to someone, I don't know if can you see my wife, if you get real up close, yeah, you're not focused, but you're averaging, and you're gonna work for your COVID test. But I want you to see this. See how this has two dots? Can you see? Can you see? I don't know if you can see it. Can you see it? There's two laser dots on it. And what that does is, as I get close to something, it's showing me, oh, look, I haven't focused yet. And then when you get right back to the right area, it turns into one dot, kind of like an aiming scope. And that's the actual distance where it's focused, right? So there's that to look at. But an even more important lie, when you think about it, is what you are looking at. And so I started, I'll do the Sears Alls last. I'll show you the Sears Alls last. And I built this little thing. This is a $1 fix to turn my $300 camera into a $12,000 camera in terms of its temperature range. And I'll tell you how to do that towards the end. But now I'll just show you some interesting lies, that your infrared thermometer says. So can you share this, Jen? I will share the iPhone. Share. iPhone, iPad. Yeah, you should be able to, it should come up in a second. All right, got it? Can you pick up the camera so I don't crush it? All right. So here's my Rebel. Let me get my pan. Yeah. All right. Wait, hopefully that'll come up in 1 second. The camera's off. All right. Now, let the camera come on. So this is a pan, a regular stainless steel pan. All right. I'm going to turn it up to 300. I'll turn it up to 300 degrees in the Fahrenheit. Oh, here we go. Did it not come on? There we go. All right. So now I want you to see something. First of all, wait, this is the actual camera. Here. Let me turn on thermal only. Thermal only. Good. This is a mirror. You see this mirror? When I look at the mirror with a thermal camera, right, I don't really see much of anything. And the reason is because something that's a mirror, right, something that's glass, right, doesn't allow the infrared light through, right? Whereas something like this, aluminum, which is not a mirror, when I look at it with the camera, I can very clearly see my reflection in it. Sorry, it's upside down. I can very clearly see if I get the image right. There's my hand, right? There's my body, there's the phone. This is all an image of me. It's not taking a temperature of the pan at all, right? And so like, I think this is an issue that everybody has when they're using infrared thermometers to cook, is they think that they're taking a picture of or a reading of the temperature, and you're only taking a measurement of the infrared, the long wave infrared radiation that's coming off of it. And things like aluminum, brightly polished things, have a very low what's called emittance. And what that means is that no matter what temperature they are, they emit a very small percentage of the infrared radiation that a normal thing, a black body, would generate. And in fact, they not only that, but they reflect. So if I'm looking into this pan here, right, and you can see I'm looking into this pan, right, you see that bright orange dot in the middle of it? Jen, can you hold this there for me? Get a good image of it. See that bright orange dot? You can see the reflection of my wife's hands in the pan. That pan is 300 degrees. The temperature of that pan is being accurately represented by the little piece of black aluminum foil that I have in it, which, by the way, that's just the orange thing that you see. Now look at just a little bit of oil, right? Because oil, even though it's is clear to us in our light, in long range infrared is completely opaque. And so it will actually form the temperature that you want. So you drip a little bit of room temperature oil into the pan, and all of a sudden you see it goes blue as it starts to heat up. And then as it spreads out in the pan, you're starting to see the actual temperature. Where the oil hasn't hit the pan yet, it's still just reflecting the ceiling, even though this orange part is the same temperature that the pan was all along, right? So then let me take some PAM spray, right? And hit it with some PAM. Ooh, look at that. Now you see how it's got that tiger striping pattern? You can't see it, but I can show you I can turn this to a visible camera here, right? In the visible camera, I don't know if you can see, it's not that bright, but there's a little air bubbles. And it's those air bubbles that are causing some of that swirl, and there's a little bit of extra oil, and you can see those kind of swirl marks in there. So, and this is why you should always put a relatively thin film of oil or something that's a good emitter, water also a decent emitter, into a pan if you're gonna try to measure it. But this got me thinking. I was thinking to myself, well, hell, that's interesting in terms of thermometers, but since we all know that the three main ways that things are heated, right, are by conduction, and conduction is when the heat energy is actually going into the, because two things are touching, right? Convection, because things are, that things are convecting, and then also radiation, right? So I was thinking, well, because I do. You're taking a thermal image of me. That's it's only at 9 frames a second. So anyway, we can put this on a non-thermal for a second. Hold a second. Camera. Here, you can just treat it like a normal camera that you're looking at here. Hold this. All right. So you're looking at this. No, just point it at me. So when you're cooking. I've been cooking in Corona. A lot of us have been cooking things. So I don't have anymore an oven that can get up to like 800 degrees. So I no longer make kind of my standard 800 degree pizza. But I do have ovens that can very easily make it up to 400, 500 degrees. And so I started doing more pan pizzas as a thing that's fun. And everybody who makes a pan pizza or Detroit pizza knows that you're supposed to use black pans, and that if you use a regular aluminum pan like this one, that the crust is not going to be as good, right? And there's lots of reasons why people say that's true, but I really wanted to test to see what was going on. And when I was experimenting with the infrared thermometer and looking at my reflection in aluminum pans and looking at aluminum pans inside of ovens and how they behave, I said, well, let's run a little experiment to really see what's going on with the black pan. Some people on the internet will say, well, the black pan is all about that they're heavy and they're steel, and so they have a higher thermal mass, yada, 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 et cetera, et cetera. Well, let's go. So I took a standard aluminum pan. The first test I ran, which I'm going to show you on the computer in a minute, the first test I ran, because whatever, it's Corona, I had sourdough, I made my own bread, it was all equally weighted. And then as I started running more tests, I was like, to hell with it. I went to Trader Joe's and bought some of their, you know, like pizza dough that off the shelf. But the 4 pans I made was I took a standard aluminum pan. Then I took one pan that I painted entirely black with Krylon high heat paint. Don't trust the high heat paint, okay? They say it's high heat and maybe it doesn't like burn, but it definitely gets sticky and you have to scrub it off of your oven racks. It's definitely not food safe. Do not use this in cooking. This is just for testing. So I had this pan that I painted on both sides black. Then I had a pan where I painted just the bottom black and left the other side aluminum. Then I had one where I painted just the inside of the pan aluminum and left the outside, the bottom empty, aluminum. And then one that I painted with quote unquote high heat white paint. So let's unshare this camera for a second and let's see what happened. I can do it up here. Stop share. And then I'll share my regular screen. So what do you think happened? Like, what do you think the difference was? And I have to say, like, once you know the theory of it, like you could deduce it from any high school physics test. But I have to say, I didn't know the answer beforehand. It was relatively surprising to me. And here it is. So this first loaf of bread on the left was the one that's cooked in a completely aluminum pan. Now, I have to say, all of these loaves of bread had the exact same starting weight to within plus or minus 1 gram. It was actually to within 1/10 of a gram, but I just don't want to seem arrogant, right? So it's a plus or minus 1 gram on these dough weights. They were all spread out onto pieces of parchment paper. The reason I used parchment paper instead of putting it directly on the pan was because, one, I didn't want to oil it like a traditional Detroit pizza because I didn't want to add that, that variable. Also, I realized from some initial tests that I did on the pans that the paint was going to get sticky, and I didn't want the paint to ruin the bottom of the thing, so I wouldn't be able to look at it. So this one on the left, I guess you could have predicted it in the standard aluminum pan, looked like garbage. It had very low rise and it had very low coloring on the crust. The second one, you can see it poofed up a lot more, and it's true, most of that was just one giant internal air bubble, but you did get more poofy, more like a pita poof out of it, and that was on the exact same style of pan, just painted black on both sides. So these are the two kind of standards, your fully aluminum pan and your black on both sides pan, like your Detroit pizza pan style, or your Chicago pizza pan if you're more of a Chicago style person. Now, interesting. Now you can clearly see that the one on the far right is much better in terms of its crust than the one in the, oh, sorry. I didn't even show you the fifth one. I'm such a dingus. I'm a dingus. Anyway, the one that looks almost identical to, the first one, the one that's the third over on the left-hand side, the one that looks kind of sallow and crappy, that is the one, and wait for it, because it was a little bit of a surprise to me, that's the one where the inside of the pan is black, right? The part that touches the pizza dough was black. And you can see that it had almost, and this one on the bottom, so that's on the bottom, you can see there are 5, and on the top, you can see there are 4. Still, the third one over, you see it's flat, and it looks almost identical to the first one. And it had almost no effect. So the black coating on the pizza pan touching the dough had almost no effect. The next one over, which looks pretty much almost as good and within the bounds of my experiment because they puffed up so much. So you see how there's a very dark and then there's a light zone. In the puffing, as it puffed away from the pan, I think I was getting not as good of a contact, and so it didn't go as well. But it's almost as good or identical to the one that's black on both sides, and that's the one that had black on the outside of the pan. And interestingly, the one that was all white, because white paint in the long-range infrared is almost as good an emitter as black, was almost as good, if not kind of equally within the bounds of my experiment, good as the other. So what this is showing is that what you're showing here is that it's the bottom that's important. So you can use an aluminum pan as long as you put something black underneath it that's touching the bottom of the pan, and you're going to get almost as good a result. And the reason why it makes perfect sense is what's happening is that your oven is heating via convection. I had convection on in this so that everything would be even within the oven because I can only cook 2 at a time. So you have convection, you have conduction, right? And then you have the radiation. So what's happening is your pan is being heated conductively and convectively, but the aluminum pan with a shiny surface towards the oven is throwing all of the radiant energy back at the oven, shunting it away, basically throwing it away, getting rid of it. So it has less ability to gather that radiant heat, and that radiant heat is clearly important enough to make a good crust. So then I said, well, what about things, because aluminum doesn't store heat very well, I said, what about things that do store heat very well? So I took a baking stone and I wrapped one baking stone entirely in aluminum, and I left one on its own because baking stones by themselves are relatively good emitters. They're almost like black paint, close enough. I let them preheat in the oven in the oven by themselves for like 45 minutes, an hour, so that they could all get to be the same temperature regardless of whether or not one was getting an initial advantage because of its absorption of radiant heat. And then I put 2 loaves on. These ones I wasn't as careful as I was in the first thing in terms of shape and all that, because the heck, you get lazy. And you can see that although the one that doesn't have the aluminum foil is clearly a nicer crust, that the one with the aluminum foil isn't as bad as it was in an aluminum pan. And that's because there is some advantage to having some stored heat in that in the baking stone. And once that heat is stored, it will get transmitted to the dough. It's just you're not getting that added advantage of the stone absorbing more radiant heat as it's cooking and being wicked into your bread. Sounds like, what about cast iron? Everyone uses cast iron, right? So I tried 2 cast iron pans. One cast iron pan I wrapped in aluminum foil, and the other one I left black, and I ran the same experiment. Let them preheat for 45 minutes or so in my oven and put the dough in. And again, I have the same thing, that the one with the aluminum foil over it is better than it would be in a thin aluminum pan, but still not as good as it is in the black pan. So it seems that there is an effect, a beneficial effect, to having a relatively large thermal mass that's hot beforehand in the terms of either a cast iron or a baking stone, but that really an important thing not to be overlooked is the emissivity of the item that you're using. Make sure it's not shiny in infrared. And so if you're using a baking steel, you want to make sure it's black. You want to make sure it's not like some piece of polished steel, and you don't want to scrub it clean in between, because aside from ruining any seasoning, you're actually ruining its point in your oven. And furthermore, let me see if I have any more of these. Here's another interesting, and I don't want to belabor this too much, but here's an interesting sidelight as I was running these experiments. So this is the black pan and the aluminum pan next to each other. Now, I noticed something. And what I noticed is that about 20 to 30 minutes after I ran my experiment, I went to go pick up my pans, and with my hands, because I knew they were cold enough by that time I wasn't going to burn myself. I do burn myself quite a lot though. So I went to go pick them up, and I noticed that the aluminum pan without paint on it was a lot warmer than the aluminum pan that was black. And then I thought about it for a minute, and then of course it made perfect sense. If the aluminum is a reflector, right? It's not a good emitter, right? Not a good absorber of infrared radiation. It's also not a good emitter. That means once it gets hot, it stays hotter longer. So here you see an experiment I ran to show that. And you can see both the black pan, here's a picture on the top, on the right, on the bottom left there. You can see that piece of black tape that I have across it. They're both the same temperature according to my infrared camera. They're both 145 degrees Celsius. I then let it sit around for a while, and I should have taken a picture earlier because the difference would have been even greater when it was higher in the cooling curve. But you can see over here on the left that even once it's cooled all the way down, almost closer to room temperature, 51 degrees Celsius, that the aluminum pan by itself has kept its heat better at 60 degrees Celsius. And this, my friends, made me think of the baked potato problem. Any of you who were alive in the 1970s, right, or their parents were, like, most of you were told that you should wrap potatoes in aluminum foil before you bake them. And I think this comes from the fact that when we used to go to restaurants and people would hand us baked potatoes, they would hand you a baked potato in aluminum foil. And your assumption was, right, your assumption was that that's how they cooked it. But in fact, according to the Idaho Potato Board, you are not supposed to cook your potato in aluminum foil. You're supposed to, as I always do, rub it in oil, salt it, and then jab a fork in it a couple times. The fork is to stop pressure from building up and exploding, and then roast it till it's done. After the potato is done, according to the Idaho Board, then you can wrap it in aluminum foil. And it's all clear to me now that the aluminum foil, when you're wrapping it after it's done, right? They give you actually a bad explanation. They say that the aluminum foil makes it steam and it ruins the outside of the potato. I mean, it's a softer outside, but that's not really the phenomenon that's the problem. That's not really the problem. But they do say correctly that wrapping a potato in aluminum foil afterwards will keep it hotter longer. So I ran this experiment for you, and these are all things that hopefully will make it into my next book, The Miracle of Moisture Management, everything I've learned about putting heat onto vegetables and meat. I'm bringing moist back, by the way. Moisture is not a bad word. Don't let anyone tell you it is. So here's 3 potatoes that I tricked out. So the potato on the right is my standard. These are actually after they're cooked. I apologize. I couldn't find a picture of before they were cooked. But inserted into each one, I have this digital thermometer into the potato center. The potatoes were, when they started, the bottom is the starting weight of the potatoes. And so you can see they're within about 4 grams of each other. The white writing on the bottom is the weight of the whole rig beforehand. And actually, yeah, that's what it is. So you jam this probe into the center. All the probes were in about the same amount. The circumference of the potatoes were all the same, and the lengths were basically the same. I went through 2 whole bags of Trader Joe's potatoes to find potatoes that I thought were close enough to run this test. They were all rubbed in oil, salt, pricked. And then this one on the far right is what I call the natural skin. That little stick sticking out of it is I put a thermocouple on the outside and jammed a toothpick into it to try to get it to stay. And also wrapped a belt around it. I don't know how to go back. Okay. The middle one is your 1970s like home cooked spud in aluminum foil. And on the right is this really cool stuff made by the Roscoe Corporation. And if you're into what? On the left is made by the Roscoe Corporation. This is cinefoil or photofoil. It is matte black foil. And while it is not food grade, as far as I know, it works great in the oven because it's meant to get next to really, really hot lights. So you can bake with it all day and nothing happens to the foil. It doesn't put any black paint onto your products. I love cinefoil. I'm a huge fan of cinefoil. For all of my black experiments, cinefoil is the answer. Plus you can clearly I can mold it around a baked potato and it's fine. So then I have the outside thermocouple. Then you can see the weight loss. So to kind of spoil the graph that's going to come up a little bit, you can see that the potato with no jacket around it it went from 279 to 223 grams, whereas both of the other ones are in the high 240s. So they lost about 20 grams less of water. That's about 10% less of its total weight in water when you're jacketing them. So they are in fact moister, or if you don't like that, soggy, because they haven't been steamed. But let's go to the graphs and see what happened. So this is a graph of the cooking. So I want you, it's kind of hard to see which ones are dashed. It's kind of a confusing graph. So I'm going to run you through it with my little line. The important ones are this blue, right? That's the thermocouple in the middle of the naked one, the natural, the shiny foil, the aluminum one. And then this orange and this purple one are the 2 ones that are wrapped. Sorry, the black foil is the purple one and the orange one is the naked skin. Let me say this again because I said it all wrong. I want to be right. I want you to be right. So this purple one here that I've got my mouse over, this is wrapped in black foil, as it says right here. This orange one is the natural skin, right, which is right here. And this one here, this blue one, is the one that's wrapped in aluminum foil. And this is minutes. So, I mean, obviously, the potatoes that are wrapped in black foil and the potatoes that are wrapped in nothing, in its natural jacket, cook at almost the same rate. The black foil, I pull them both as soon as the thermometers hit 98 degrees Celsius. The black foil one was done 1 minute, not even a full minute, like 45 seconds after the one, or before the one that was natural. So those all came out within a minute. But you can see that in order to make it up to 98 degrees, instead of being done in 40-something minutes, which these were, the one that was in aluminum foil took over 60 minutes to make it up to that temperature. So it's going to take you a lot longer to make it up to your final cooking temperature. And then if you want to look here, the problem is that this orange one is fairly accurate because this thermocouple was sitting in the oven. Both the black foil thermocouple that was on top of the potato and the one that was in the aluminum foil, you can see like we had an issue. I think it got caught in a pocket and got insulated or something. So instead of topping out close to here, it topped out, you know, well below 100. So I don't really trust these numbers, but I'm just showing you that they track pretty well. This porpoising is actually, because it's so close to the foil, is the porpoising of the oven temperature as it's heating up and down versus the relatively smooth curves that you see here. But what's more interesting is if you take a curve and you look at them as they're cooling, right? Notice that the black foil, right? Sorry, let me get this exactly right. The natural skin, which is this green thing, or yellow, it's hard for me to tell on my computer. This green thing cools very, very quickly, much quicker than the one with the black foil, which is this blue line. Now the black foil, remember, the only difference between the black foil and natural skin, they have almost the same emittance, right? So the only reason, if I go back here, oops, the reason that these two potatoes, both the natural one and the black foil, cook so much faster than the aluminum is not because, as people say, it gets steamed. It's for no other reason. This extra boost in time is only because of the radiant heat that the potato is absorbing that is not being absorbed by the one that has aluminum. So then if you go forward and you look here, right, the difference between the black foil and the natural skin on the cooling, right, is that the oven is hot enough to overcome any evaporative cooling and just ride right through it and push the potato up to its temperature. So they cook at almost the same rate. When they are cooling, as liquid is evaporating off the surface of the natural skin potato, it cools very quickly and possibly loses a lot of its water weight during that cool off period. So here is where the Potato Council is 100% correct. You will see that you want to wrap your product in shiny foil, which is this red line, because it keeps your potato hot the longest. Notice the black foil, because it's a better radiator, right, cools faster than the shiny foil, but because it does not allow for evaporative cooling, it cools a lot slower than the one that's in the air. And so this is, that is what, and these are the three potatoes. On the right, it's a shiny one in the middle, black on the left, and natural on the right. And this is what playing with my infrared thermometer has taught me about baked potatoes. So if do I have any time left or am I done? What do you guys, do I have any time left or am I done? Do I have time left or done? Time left, done. You want to see a quick, tiny bit? All right, let's get the infrared thermometer back online, see whether we can get this thing going. Get the share going, Jen. It's a very kludgy system, people. Screen mirroring, Zoom. Okay. And then, tell me when it comes up, and I'll start talking about this. So back to Sears Alls. I don't have time to run this demo, but I'll just show you what it was. I wanted to test to see, remember the Sears All is this infrared broiler that I make. It's coming alive. And I wanted to see how much of the energy from the Sears All is radiant and how much is conductive and convective. So I made this little test rig, which you can see here, which is the black foil and the aluminum foil with a thermocouple underneath with equal thermal load blocks underneath them. And if you go back so you can see both, you can see this is reflective. Well, you can't, it's too complicated to explain. But anyway, it turns out that it's almost all radiant, and that the thermocouple underneath the aluminum foil doesn't hardly heat at all. So if you do use a Sears All at home, a couple layers of aluminum foil and a little bit of space off of your stuff will protect anything that you need to protect at home. But let's take a look at this. So here's the problem. Take a look, Jen, at this. No, this. All right, you see how it's like basically completely saturated? It can't take a picture of it. It doesn't know. And the reason is because you have, I'm trying to get the temperature range different. The reason that happens is because this camera is only specified to take pictures up to 400 degrees Celsius. So you can see it hasn't fully heated past 400. But now if you look in the center, it's all, make sure you look at the, make sure you're getting the eye of the Sears All. Make sure you're getting that. Yeah. You see how there's no definition? It's just one color because you saturated the camera out. It's at 400 degrees Celsius and you can't go any higher than that. Now, I wanted a camera that would do like 1,000 degrees Celsius. The problem is 1,200 degrees Celsius. The problem is those cameras are like $10,000, $20,000 to get something that will accurately record those temperatures. But here's the trick. Here's where you can mess with them, right? Remember that a thermal camera, an infrared camera, is merely an optical system, right? And remember that what it's doing, remember back to that graph I showed you, is it's integrating the area under the energy curve and computing what the temperature is. So if you think about photography, I hope you guys have heard of the thing called a neutral density filter. And what a neutral density filter does is instead of like a red filter or a blue filter, which filters out certain wavelengths of light, it filters out all of the wavelengths of light in the area of interest to a certain degree. It's like sunglasses with no tint. That's what a neutral density filter is. So if you can use an infrared neutral density filter, you're lowering the amount of radiation coming from everything and therefore tricking the camera into thinking that everything is a lot cooler than it is. So it's more complicated than this, but roughly, if I cut half of the infrared light out, I'm cutting out, I'm basically doubling the temperature that the camera can see. Now, you have, remember I showed you that like things aren't what they appear. Glass is opaque in infrared, right? Usually, you use very fancy things when you're doing science with infrared. You use an element called germanium, which is incredibly expensive to buy. Neutral density germanium filters, a tiny half-inch filter, 1/16 of an inch thick, is like $200 from my discount place. If you go to Edmunds like Scientific, it's like $300, and I bought the wrong one. Really irritating. But you know what's almost perfect in the long wave infrared that FLIR uses? Do you know what's a really good? It only has a couple of spikes that are bad, and you can just ignore them. Quart container lids. Watch this. So you're looking at the thermal camera, and you know all the temperatures are what they are. And then I put a quart container lid, and oh look, the temperatures just go down, right? See, bring it up, they go down. So the quart container lid, just this simple, cheap, almost free, high-density polyethylene quart container lid, if I put that over the camera, I built a little, you know, I 3D printed a little thing, right? So now the camera is, and I know it looks darker, everything looks crazy. And the reason it still says 34 is, this is where it gets a little more complicated. The camera is also taking into account the fact that the optics within the camera are radiating infrared back. So it's pretty much averaging everything around what the atmospheric temperature is. But when I go to higher temperatures, you'll see. Watch now. Now you see how I'm still getting a full read across my entire Sears All, even though, and you see how the upper temperature that it's reading is only 224 degrees, right? I happen to know that this thing is rocking up around 1,000 degrees Celsius, right? I still haven't saturated it out. So I have taken my $300 FLIR camera, and by the way, they're real jerks about this. They won't tell you anything about it because they really, really want you to buy the $12,000 camera. But if you take just a couple of pieces of quart container, only one if you're measuring normal grills, but if you're doing something like I'm doing, 2 pieces of the quart container, you can take pictures. It takes a lot of calibration, which I can tell you about offline if you care about it. and you can turn your crap or your low priced, your inexpensive consumer budget camera into one that can take pictures of very hot things. That's it. Everyone else is still muted. No, they do that.
Everyone else is muted. I think I finally got my voice back. Thank you. And I hope you can hear our applause over Zoom.
That was great.
Oh, nice.
Awesome.
And your students should totally do that. Use the cheap cameras and just use things that they can find around for filters to jack the temperature, you know?
So we can take some questions, Pia?
Yeah, we have some questions. So thank you to both Harold and Dave. And we didn't get a chance to clap for Harold, so we'll clap extra long for Harold now. Thank you both. That was fantastic. And I want to say, I have a few things to say to our attendees. So first of all, thank you for being here. This is fantastic. It's crazy to think that there's sort of this community out there and we can't even see you. Number two, thank you for your patience. I know that there have been some audio issues, all kinds of issues. Turns out that even with 6 months of teaching on Zoom, there are still curveballs from Zoom. So thank you for being patient with that as we figure it out. What else? There's a number of questions asking if we're recording this. Yes, we are. You can go and enjoy it all again. And we will be posting it on our YouTube channel and we'll send out a link to you. We have your emails, so you can go and find it. What else? Okay, so I think we have just a few minutes for Q&A. And if you haven't yet located the Q&A button, there's a little button, for me it's in the lower bar. You can just type in your question there and we will read them to Harold and Dave. So I have one of the first questions came from Paulina, it's for you, Harold. And the question is there anything like a half-life of smell, or is there a smell that lasts forever?
That's a really interesting question. So there's the half-life or the lifetime of the substance that we're smelling, and then there's the half-time of our response to what it is that we're smelling. And it turns out that even if a volatile molecule is present at the same concentration continuously, our response to it goes down because we adapt to it. Our brain decides that if it's there all the time, then it's kind of background information. We don't really need to pay attention to it. So our perception of it declines with time. The perception part of smell is something that I intentionally left out of this book because it's fascinating, but it's complicated, and it kind of boils down to a very simple thing, which is you never know what you're going to smell. You can be presented with the same molecules under two different circumstances, and one time you'll notice them and the other time you won't. So what I was interested in doing was describing what's out there, whether or not you're ready to detect it.
Harold, can I add something? It's known to perfume companies that if you want somebody to smell a perfume after they're used to it, you have to add 10 times as much. That's just one fact for the same smell.
Yes, yeah.
Right, perception is very complicated.
So the next question is for you, Dave, there's a number of questions actually, and so maybe I can group them together. One of them is about what about a transparent glass pan? And another one is, would this translate to a black pizza stone? And then another one is aluminum has good conductivity. So when we bake with aluminum, it doesn't actually heat up or cool down faster. So I don't know if you want to kind of lump them together if you're able to summarize for those.
Yeah, Pia, tell me if I miss one, okay? So a glass pan, I haven't fully checked it yet. The glass is interesting because it's thick. It has a big thermal mass, right? And it holds heat well, because it's not actually a fantastic conductor. However, it is a good emitter in the long-range infrared. Regular glass that you use in baking dishes is opaque to infrared, so it does absorb the radiation good. And if you think about it, that's why it takes a while for one of those glass pans to get it going. But once it does get it going, it holds the heat and does in fact make a nice brown, or can sometimes over brown your stuff. But it takes a lot longer for it to heat up. Regarding aluminum, what was the second one, Pia? What was the second part of the question? While you're getting that, I'll get the aluminum one out of the way. Aluminum is a great conductor of heat, right? But on the other hand, and it's usually there's relatively thick, so there's a lot of metal there, but there's not as much kind of material there. It's not very dense, so it's not storing that much. So the trick is with aluminum is it's going to be the fastest, the fastest cheap, inexpensive metal, right? That will get, if you apply with a conductor heat on the bottom, right? If you conduct heat into the aluminum, it will transmit and then conduct to the food very fast, much faster than steel, much, much faster than stainless steel. Not as fast as copper, not nearly as fast as silver if you have that kind of money. But on the other hand, it will not be absorbing any of the radiant heat off of your oven, which is why your ovens are black typically. Or if you're putting a liner in your oven, it's actually better to line your oven on the bottom, not with, well, think about it this way. If you have a heating element in your, if your heating element is underneath your oven, right? Like an old gas oven, right? Then you want the bottom of your oven to be black, because you want it to radiate up, or enamel, which is black and infrared. If your heating element is above, so in a toaster oven like a Breville or a Smart oven, right? The bottom of the rest, this part of the oven is all black or enamel, and the bottom tray is aluminized because they want everything from the quartz heating elements to reflect back up. So you can play with it a little bit, but anyway, I hope that answered the question a little bit. Is that once it's conducting, aluminum's great, but you're going to get a very slow input of heat in, because it's not accepting any of the radiant heat. What was the middle question, Pia? I missed the middle question. I got the first question and the last question, but the middle question escaped me. I can't hear. I can't. She's
muted. Yeah.
Yeah. She's still muted.
You're muted, Pia.
Yeah. Can I unmute her? No. Can Patricia unmute her? Pia's muted. Pia, you are muted. Anyway.
No, I cannot unmute her. Neither.
Dave, do you remember what the middle question was?
Did you answer the glass pan?
I answered the glass pan. What about cast iron pizza?
I can speak now. Glass pan, black pizza stone, and the aluminum.
So black pizza stone, I've been thinking about this. Look, when you look at emissivities, and I encourage you to just go on the interwebs and look for emissivity charts, because there's tons of them all over the internet. The problem is that you better make sure that the emissivity chart you're looking at is calibrated for the wavelength in question, right? So, if it's extremely emissive in a wavelength that's not important for like 400 to 500 degrees Fahrenheit, which is what we're dealing with, it's not going to be useful. But most baking stones are relatively emissive. Now, what's not 100% a great emitter is fire brick. So fire brick, not a great emitter. So, depending on which one. So what I would do is, if you have a thermal camera, it's easy to take a picture of your baking stone versus a known good emitter. And the standard that FLIR uses is Scotch the thick Scotch black electrical tape, very good emitter. But my guess is that your baking stone, that the people who make it have thought about this, and even though it's not black colored, it's a fairly good emitter. And so you're probably talking about 1 or 2% difference, which is not a lot. It's not going to help you that much. So like to think about it this way, like the emittance of like a pure shiny aluminum pan is like less than 0.2. Okay, less than 0.2, whereas like a baking stone might have an emissivity of something like 0.95. So if you're taking it up to like 0.96, it's not going to help it that much. So I would say it's not necessarily going to be a winning proposition. It's not going to hurt you, but it's not going to be a winning proposition.
Great, thank you. So we have a number of questions. And for you, Harold, they're kind of related. So one of them is, can we manipulate smell to enhance the perception of flavors? And then a connected one is, how many smells can someone accurately judge at once?
Okay, well, so both of those are kind of veering in the direction that I intentionally avoided writing about, but I still know something about them and have opinions and that kind of thing. So the first question was about enhancing flavor with smells. And so there have been famous examples of chefs, for example, serving a dish on a pillow where there's an aromatic inside, and as the weight of the dish slowly depresses the pillow, the aroma is released and surrounds the dish. The thing is that when we sense aromas, we're sensing them when we're breathing. And when we sense an aroma in the air over the plate, we're breathing in. When we sense the aroma of a bite of the food that was on that plate, we're breathing out. So we're not actually mixing the two, we're experiencing them sequentially. And there's probably an enhancing effect, maybe a little carryover, maybe, but it's a complicated thing. It's not like simply adding another ingredient to a dish. And it hasn't been that well studied. So I think that's a very interesting thing to look more deeply into. And now I've forgotten, since I've gone off that long, I've forgotten what the second question was.
How many we can judge at once?
Ah, yes. The answer to that is not very many. And so these were experiments that were done in the 1990s, and then they've been repeated over the decades, and pretty much the same result is coming up, where if you give trained flavorists, trained perfumers, and ordinary people mixtures of pure molecules, after the third or fourth, they can't really pick out what's in there because for all kinds of reasons. The thing is that's a very, and so that those results are used to say, well, so these people who find 20 different aromas in a wine, they're just making it up. But in fact, that experiment doesn't take into account all the other things that are going on when you do something like taste a wine or food or anything particular that you like, which is that you're not tasting a small handful of pure chemicals. You're actually dealing with a complicated mix. It's, in the case of wine, for example, it's evaporating off the surface, and that changes with time. I'm sure everyone's had the experience of the same thing tasting or smelling very different 5 or 10 minutes after you've had it the first time. Dave, I'm sure, has plenty of anecdotes about how the temperature changes in a cocktail that's sitting on the bar while you're yakking with your neighbor, changes the relative volatilities of things and the overall flavor. So these results that say we can only detect 3 or 4, I think, they're an interesting benchmark, but they don't really reflect the reality of eating and drinking. And we can probably appreciate many more than that. That would be my guess.
Okay, great, thank you. So we have been going for 2 hours, and the questions keep pouring in, but I think I worry that we're going to exhaust you guys. So I think we should probably stick, unless I hear a strong disagreement, I think we should probably wrap up here and kind of end this officially. And this will be recorded and posted, so you can go back. And I noticed that a lot of the questions actually in the Q&A are things that I know the answers are out there. And I know that they're in Harold's book, they're in Dave Arnold's books, they're also in other people's books who are thinking about flavor, who are thinking about the science of the things Dave Arnold talked about. So I suggest that we end here, and I will send you guys on a mission to find those answers. And thank you so much for coming. And thank you again, Harold and Dave.
Thank you, guys.
Thanks for having us.
Yeah, a pleasure. Next year in Cambridge.
Yeah, and if you have any questions you desperately need, go to Cooking Issues, my Twitter, and I'll answer them on my weekly podcast. Any technical, weird cooking questions.
Thank you, Pia.
Thanks.
Thank you, Mike.